Hi, welcome back to Advent of Code 2022. This is day 10. Hope you guys are enjoying these videos. I'm enjoying making them for you. So yeah, let's get started using Python 3, solving Advent day 10. I'm happy we're in double digits. Things are going to start to get a little more difficult, and I'm pretty stoked about it. Let's go. You avoid the ropes. Oh, a cathode ray tube. You avoid the ropes, plunge into the river, and swim to shore. The elves yell something about meeting back up with them upriver, but the river is too loud to tell exactly what they're saying. They finish crossing the bridge and disappear from view. Situations like this must be why the elves prioritized getting the communication system on your handheld device working. You pull it out of its pack, but the amount of water slowly draining from a big crack in its screen tells you it probably won't be of much immediate use. Unless, that is, you can design a replacement for the device's video system. It seems to be some sort of cathode ray tube, an old CRT, screen and simple CPU that are both driven by a precise clock circuit. The clock circuit ticks at a constant rate. Each tick is called a cycle. Start by figuring out the signal being sent by the CPU. The CPU has a single register X, which starts with the value 1. It supports only 2 instructions. Add XV takes 2 cycles to complete. After 2 cycles, the X register is increased by the value V. V can be negative. No op takes 1 cycle to complete. It has no other effect. The CPU uses these instructions in a program or puzzle input to somehow tell the screen what to draw. Consider the following small program, which is of course our example. Execution of this program proceeds as follows. At the start, it runs a no op. And then during the first cycle, X is 1. Right? At the start of the second cycle, add X, and then after 2 more cycles, X is 4. And then the 4th cycle, we add X -5. And then after the 5th cycle, X is -1. Maybe you can learn something by looking at the value of the X register throughout execution. For now, consider the signal strength, the cycle number multiplied by the value in the X register. Okay, during the 20th cycle and every 40 cycles after that, that is 20th, 60th, 100th, 40th. For example, consider this larger program. We'll grab this guy, this larger program as example 2. This interesting signal strength can be determined as follows. During the 20th cycle, X has value 21, so the signal strength is 420. And then during the 60th cycle, goes up and up, up. Sum of these signal strengths is 13140. Find the signal strength during the 20th all the way up to the 220th cycle. Okay, let's grab the puzzle input. Okay, I believe we're ready to go. So every year during Advent, if you guys haven't done these before, every year there's usually one problem that kind of makes you sort of do instruction like build a new computer or some sort of weird computer, and it happens over multiple days. So there'll be a set of like 3 problems over the course of the whole 25 days. They use the same sort of input and make it more complicated each time. My suspicion is that this system, the no-op and add X instructions, will be something we redo over and over again, maybe 2 more times. So I'm going to be pretty pedantic or make sure that I read these inputs very well and that they're nice and structured so that the next time we can reuse this code. So we're going to have to remember day 10 is when we did the instructions. So let's start with, as always, reading in our input. So our input is going to be a program which has a list of instructions. An instruction has a I would really like a algebraic type system right here where you could say it's either no-op or it's add X. So an instruction is, let's just do a pass. Let's make instruction like a base class, and then we do, does this work? Class no-op is an instruction. I wonder if this works. And pass, and then, well, cycles is 1. So it takes 1 cycle to complete. So this is our base class instruction. Class add x is instruction, and it has cycles 2, and it has a parameter. Oh, we'll do instruction. Oh, I see what we're gonna do. We're gonna do command. We're gonna have command, and we're gonna have params. And this is gonna be a list of int. Yeah, okay. And from import enum, class command enum.enum, and we have no-op equals no-op, and addx equals addx. All right, so now we have our instruction, and we want to do def cycles. Actually, cycles are on the command, so def cycles self, if self equals no-op, self.no-op, then return 1, else elif self equals self.addx, return 2, return 0 otherwise. Cool, and then, all right, so now we have our set of instructions. Cool, so this will help us later when we're like doing things, and maybe we can expand it to multiple kinds of instructions later. So let's just parse this input. Input is a program, list of instruction, and we do instruction.parse instruction line. So we'll make the init of this function self line string. We'll make this initialize. So first we do command equals command on we'll do command s comma rest equals line.split 1. So, or sorry, space and then 1. So this will split on space, but actually we want to do space, and then we want to do star rest here. So we get the rest of the instructions by, everything else after the space will come in a list. And then we do command equals command on command s, so the string version of command, and params, self.params equals int p for p in rest, and self.command here. All right, so now we've initialized everything, so we can do the instruction. Awesome. So we've done parse input. Now we need to execute. So we are going to make a, what is this device called? Some sort of device. So we'll just call it a device. Class device. Okay, and it has a state. And the state has a register x. X is 1 upon initialization, right? Int, and then cycle is an int, and that starts at 0. And you can execute instruction. Def execute self instruction, and that modifies itself. All right, so if inst dot all right, command, all right, so cycles equals, how many cycles? inst.command.cycles, right? So we get the number of cycles that this instruction takes. And then we do if inst.command equals command.noop cycle cycle plus equals 1, and we return, we're done. Elif inst.command equals command dot add x. I guess we don't need this cycles thing here. We'll just embed it later. We'll do cycle plus equals 1. Yep. And we'll do self dot cycle and self. So then we'll do self dot cycle, not cycle, but like increase cycle. Cycle starting to look like misspelling, but I guess it's not. Increment cycle, that's what we'll call it. So we're going to increment the cycle with a function. We're going to increment the cycle, and we're going to do x equals 1 here. X equals self.x plus inst.param 0. All right, so what are we doing here? We're going to make this def increment cycle function, self x equals x optional int equals none. All right, so what does this do? It increments the cycle by 1 and sets the x register if it's set. So if x self.x equals x, else, and then otherwise it's cycle plus equals 1. And then we want to, during this thing, we want to track every 20th step, right? So we have a list of values for every 20 steps. So every 40 steps. So signal strength, signal strength. List int, and that starts as an empty list. And then we, in our increment cycle, if cycle minus 20 modulus 40 is equal to 0, then signal strength plus equals what is signal strength? The self.x times cycle. Okay, so that's signal strength. All right, and then we add it to that list of signal strengths. Awesome. All right, so that should be good to go. So now we're ready to execute, because this should handle everything in our program. So we're gonna do device equals device. We're gonna initialize our device, and then we do for instruction in input.program device.execute the instruction, and then return device.signal strength. And we only want the first 6 values, and we just sum it. Okay, let's run that on our example input, the larger one. Python day 10, example 1, no, example 2. All right, command is no attribute cycles. Right, we can remove this. Local variable cycle in increment cycle, self.cycle and self.cycle and self.cycle. Got it? Device has no attribute x. Did you mean x? There it is, x. Local variable signal strength reference before self dot. All right. We're getting it. We're getting it. All right, 13,360. We have 13,140, so we did something wrong. Let's import IPDB. IPDB.set trace. Oh. We're just gonna install our debugger. I was trying to mess with my Python environment the other day, so. All right, so now we are debugging. Go to the top of the, this is pretty small for you guys, I bet, so I'm gonna blow it up and make it smaller at the same time. All right, so we set a trace. Now I just wanna look at the device.signal strength and see where we're off. So 420 matches, 1140 matches, 1800 matches, 2940 matches, 2880 matches, but the last one is 3960, but this says 4180. That is weird. So it's in the 200, it's in the last 40 cycles we got something wrong. So wait, what is 4180 divided by 220? That's 19. So we have 19 in the register. It says 18. I wonder if we are just like an off by 1. So we have set X in our increment cycle and incremented the cycle at the same time, then calculated the signal strength. So let's go back and reread very carefully. At the start of the fourth cycle, add X -5, instruction begins execution. During the fourth cycle, X is still 4. So that's what happens when we do add X here. Increment cycle. Then during the fifth cycle, X is still 4. After the fifth cycle, add X5, finishes execution, setting X to -5. Okay, so what we did wrong is that we set X before we calculated signal strength. So let's move to setting X at the end of the cycle, as is desired. Remove our debugger statement and execute again. And we get the correct answer. So I'm willing to bet that we have the correct answer now. So I'm running it on the input and pasting it in. It's not the right answer. Our answer is too high. So we got it wrong again. Cool. So what did we do wrong? We're going to have to debug this guy. But we got the example correct. So how are we going to do this? Let's reread a little bit and make sure that we did everything correctly. Okay, so signal strength is calculated during the cycle. So okay, our cycle starts at let's just start by printing every increment cycle. Let's run on the example. I'm going to go up to the top here. Increment cycle So cycle 1, value 1. Cycle 2, during is 1, and then at the end is 16. And then cycle 3 will be 16, 16 until negative 11, and then 5. And this seems very correct. Let's consider our input. What happens during our input? We have 3 no-ops. You know what? Let's put this on the end and rerun on the input. So in our first cycle where we calculate signal strength, it is cycle 20 and we have value 10. So let's go through that. So we have no up, no up, no up. So that's 1, 2, 3. Then add x 4 times is going to be 1, 2, 3, 4 is going to be 8 cycles long. So 1, 2, 3, 4, 5, 6, 7, 8. And afterwards, we will add 4 plus 1 is 5, plus 3 is 8, plus 3 is 11, plus 3 is 14. And so that's what we get. So after this cycle, after the 12th cycle, after the 11th cycle, we have the value 14. Then we have a no-op, so that's 13th cycle. Then we have 2 and 1, so 1, 2, 1, 2, 1. Now we're at the end of the 16th cycle, we're at 17. Then we have negative 7, so at the end of the 18th cycle, we are at 10. And then we have 10. And so during the 20th cycle, we have value 10. That seems correct. Okay, so we did all that. We added it up. How far do we go? Let's just keep going. Oops. 180, 220. So it goes all the way to 240. The 20th cycle occurs in the middle of the second at x negative 1. So the value of the register is the starting value, 1, plus all of the other at x values up to that point. I suppose you could definitely not execute these instructions like this. You could just figure out which instruction happens during that cycle and add up the values. But we're just trying to execute it as instructed. What? Wait, what happened? Okay, I just cleaned up the code and I didn't think that would cause a difference, but it did cause a difference in the output. What did we do? So I decided to clean up this implementation. I figured, okay, incrementing the cycle has no effect on X. X changes at the end of the cycle. So I figured we could clean up the cycle by moving self.x, and we'll do a plus equals inst.params 0, which should set X to X plus the params, or the first parameter, at the end of increment cycle. Right? So we save this, we run it. On the input, we get 23660. I'm going to remove this print line. Okay, and then if I remove this as a parameter, sorry, my auto commenting isn't working right now, and make this self.x happen outside of the increment cycle function, I get a lower number. Why? I don't get it. I mean, I'm going to submit it because I think it's correct. It is correct. And we can move on to part 2. I just don't understand why, though. Are we double counting? Were we double counting things? I don't see it. I'm going to have to come back to it, but I'm glad we got it right, I guess. Yeah. Let's clean this up and move on to part 2. It seems like the X register controls the horizontal position of a sprite. Specifically, the sprite is 3 pixels wide. The X register sets the horizontal position to the middle of that sprite. In this system, there's no such thing as vertical position. The sprite's horizontal position puts its pixels where the CRT is currently drawing. And then those pixels will be drawn. You count the pixels in the CRT, 40 wide and 6 high. CRT screen draws the top row of pixels left to right, then the row below that, and so on. So left to right. The leftmost pixel in each row is position 0. The rightmost pixel is position 39. Like this, and then it goes down, so it's 0 to 5. Like the CPU, the CRT is tied to the clock circuit. The CRT draws a single pixel during each cycle, representing each pixel of the screen as a pound. Here are the cycles during which the first and last pixel in each row are drawn. All right, so it takes 40 cycles to draw the first one, etc., etc. So by carefully timing the CPU instruction and the CRT drawing operations, you should be able to determine whether the sprite is visible the instant the pixel is drawn. If the sprite is positioned such that one of its 3 pixels lies on the pixel currently being drawn, the screen produces a lit pixel. Otherwise, the screen leaves the pixel dark. So during 240 cycles, it draws the screen once. The first few pixels from the larger example are drawn as follows. 1, 2, 3, because it is in position 1. So 0, 1, 2 are all drawn. Okay, cool. I think we can do this. And we're just going to have to count lit pixels, right? Allowing the program to run to completion causes the CRT to produce the following image. Render your image for the program. Which 8 capital letters appear in your CRT? Oh, this is fun. All right, so we actually have to render the image, which is very cool. So during each cycle, we draw the image, right? So we're going to keep an image in our device, and it is going to have a, it's in matrix, so it's a list of int, which equals actually list of bool, which equals false for I in range 40 for j. We'll do I for j in range 6. I like to keep I as the first parameter, so as the outer parameter. So, all right. So now we have a 6x40 image, and we're going to draw on it. So if we'll do self.draw def draw self. If so we get the I parameter, which is going to be our vertical parameter. So that is equals self.cycle divided by 40. And then we get our horizontal position, which is j. That equals self.cycle minus I times 40. Actually, we just need the modulus of 40. And that'll get us our horizontal position. So then we want to do want to do self.image at I and j equals if self.x minus j. So if self is the absolute value of their position, if the position x is less than or equal to 1. So if x is j, or it's j plus 1, or it's j minus 1, then we draw true. And otherwise we draw false. And then at the end we want to print. So I'm going to make a string function, and I'm going to move all these part 2 things down below so that we know they're all part 2s, right? What did I do? Whoops. I was like, too much disappeared there. All right. And then we're going to do part 2. All right. So now our string function return new line dot join and then we're going to do dot join. We're going to do each row, and we're going to do dot pound, or do pound if cell else dot for cell in row, for row in self dot image. Nice. And then part 2 is we just execute the instructions, and then we will just print our device. And that should give us our answer. Run it on the example 2, list index out of range. Cycle starts at 1, and we want to do -1. So cycle equals self.cycle minus 1. Okay, let's see if we drew that right. That looks very correct. Awesome. Let's do on the input. Okay, yeah, this looks right. So we got REHPRLUB. Double check. REHPRLUB. All right, let's answer. We did it. We got it right. So that was cool. That was fun. I like drawing the answer here. I love when they make us draw the answer. I think it's really cool. You got to interpret it. So that's really awesome. I really don't understand why setting x in our increment cycle function was different than setting x outside our increment cycle function. You know, the only difference I can think is that you pre-calculate based on the value of self.x here, and then you set it here, but it never changes in this function. And yeah, that's just really baffling to me, how passing x into here and doing it down below is different than doing it here. The only thing I can think of is that if x was being modified 2 lines below, that there's some sort of delayed calculation, but that doesn't even make sense. So yeah, I'm not entirely sure why we had a bug. And sometimes that's just how it is. If you guys know why I had a bug, feel free to let me know in the comments. I'm pretty baffled, but I'm happy we got it right. So let's just move on. I'm gonna go for my run today, and I'm gonna think about this. But I guess I'll see you guys tomorrow, day 11, into the more difficult problems, and I'm happy about it. I'll see you then. Bye.